everyone to the last TIMS seminar of this semester. And if anyone has anyone that they especially want to hear from or any topic they want to hear about next semester, let me or Edmund or Brian know so that we can try and get the people in because we're still working on the schedule for next semester. Today we are going to hear from Bob Hallberg from the Geophysical Fluid Dynamics Laboratory at Princeton University down in the great state of New Jersey. And he's going to tell us about the ocean boundary layer turbulence and climate models. So this is going to be, I think it should be interesting for the people in atmospheric science because there are lots of commonalities between the planetary boundary layer in the atmosphere and in the ocean, but there's a lot of differences too. So it's worth seeing how the two are contrasted and trying to model one versus the other. Bob initially got his degree in physics from the University of Chicago back in 1990, and then went on to the University of Washington, got a PhD with Peter Rines, and then became UCAR ocean modeling postdoc fellow at GFDL in 1995, and has been there ever since. Became a staff member in 97, and since then has become leader of the Ocean Climate Group, co-leader of the Ocean Modeling Group, and has gotten a lecture appointment at Princeton University as well, where he teaches modeling of the ocean atmosphere. He's done a lot of work on dense overflows, mesoscale eddies, and ocean ice shelf interactions, and developed several ocean models primarily by himself, and then has been a major contributor to the GFDL's ocean model. And a number of you in the atmospheric sciences might not know about the tradition of giving ocean models silly names in physical oceanography. So one of the old, well, it's still around, it's still being updated, but one of the classic models for climate scale ocean modeling is called the Parallel Ocean Program, or POP, and that is primarily developed by the Department of Energy. And then GFDL's ocean model is called MOM, or the Modular Ocean Model. And then Bob wrote a model called the Hallberg isopycnic, or is it isopycnic model, which is him. And what I want to know is when are we going to get through? So
the sea ice model at GFDL is the sea ice simulator, right? So that's, and then the land model is, I don't know what it's called, but it's the land something dynamics. So assisted labs. So we have the whole family of models. Of course, Mom is the mother of them all. Pop was
Pop based on Mom?
Pop was derived from Mom. So anyway, that's not what I really wanted to talk about. So instead, today I wanted to spend a little bit of time talking about the physics of the ocean boundary layer, how it's represented in climate models. And this is motivated in part by our recent experience going and developing a completely new coupled model and finding that as we pushed to higher resolution, we were getting these weird instabilities that turned out to be things that were partly coupled, fundamentally coupled instabilities between the ice and the ocean, and partly because we're using the same representations of the ocean boundary layer that we've been using for the past 20 years. And so this was a chance to go back, and the deeper we delved into what we have been doing, the more we thought, it's time to go back and reconsider the problem as a whole, think about whether we can do this in a way that ironically gets closer to the original physical roots of what people have done. The boundary layer problem is something that people have been working on for a very long time. There are some classic papers, kind of summaries of the whole field, going back into the 1970s. And if you read them even today, they're still a really nice description of a lot of the physical processes that are going on in a one-dimensional context. Over time, we've come to appreciate that there are a wide variety of processes that are important to get involved. A lot of this is driven by newer, higher resolution data, higher resolution in time, higher resolution in space, better sampling, and beginning to appreciate some of the complexities of what's going on. But rather than focusing on the complexity, today I'm going to be taking a perspective that's a little bit pedagogical, but intended for a very broad and diverse audience to get you to the point where you can appreciate from some pretty fundamental physical principles what's going on in the boundary layer. So I'm not going to be getting into too much jargon. I think we have a tendency sometimes to mimic physicians who will see, oh, you have a bruise, but they'll call it a hematoma as though that means that there's something else. Well, a bruise is a bruise, and that's good enough. So I'm going to try to keep the language simple, and I'm going to try to keep it approachable. If I get into jargon that is getting a little bit beyond your understanding, please stop me. I'm going to try to avoid that. The basic background behind all of this that I'm assuming is that you've had maybe a high school or college physics course, because the physics behind this really is mostly that simple. If you describe it the right way, you should be able to understand it. Some of the more recent things tend to make things look much more horrible than they really are. So the broad outline, I'm going to spend just a few minutes talking about why the boundary layer matters for climate problems. This was maybe a little bit obvious, so I'll go through that kind of quickly, but the bottom line is it's enormously important at all time scales. I'm going to spend some time talking about the physical processes that are going on, and hopefully by the end of this section you'll have a feel for the physical processes and the balances that matter, and this should be pretty tractable. I'll spend a little bit of time talking about how we've represented the boundary layer in climate models now and in the past, and what are the challenges. So this is the part where it might get a little bit thick in the weeds, but bear with me, because in the end, I'll be coming to a brilliant new approach that solves all the problems, and that after listening to the first part, you will all understand and be completely convinced of. Right, so the ocean is a complicated place, and there are lots of processes that you have to take into account in understanding how it works and its role in the climate system. And this is kind of a cartoon emphasizing just the wide range of different processes going on. The ocean is a force system. A lot of what you see is the ocean's response to atmospheric forcing in terms of wind stresses, in terms of heat fluxes, precipitation, radiation, and also interactions with the sea ice. There are interesting interactions going on. There are a lot of fundamental physical processes that take place. Things like Ekman transport and Ekman spirals, the effects of rotation, are important in the boundary layer. But this boundary layer is really critical for the long-term climate problem, because this is what mediates the interaction between the atmosphere and the ocean. And the ocean is where all the storage, all the long-term memory in the system arises. So the atmosphere is this flighty, fast, ephemeral thing. The ocean is slow and massive. But it's a rather different boundary layer than the atmospheric boundary layer. The atmospheric boundary layer, if you have to ask an atmospheric scientist, what do you care about from the ocean? They'll say, well, what's the temperature? Okay. What else? What's the temperature? Anything else? Temperature. And after about 5 or 6 times, they might say, well, is it rough and wavy or is it moving? But it's mostly the sea surface temperature that the atmosphere really cares about. And so if you just prescribe this bottom boundary condition to the atmosphere, that's a pretty good head start in being able to describe the external influences on the boundary layer. The ocean is completely the opposite. The ocean is forced by the atmosphere. The ocean is driven by fluxes from above. The internal dynamics are there. They're important, but not to the same extent as they are in the atmosphere. And so instead, the way that we want to model the ocean, I think, is by paying attention to the constraints that come from the imposed forcing more than things that empirically emphasize the internal dynamics. Okay? And in terms of the climate dynamics, the ocean is where all the heat capacity in the system is. There's some in the land, there's some in the cryosphere. But the topmost 2.5 meters of seawater has the same heat capacity as the entire atmosphere. So this is why, if you look at the temperature over the ocean, it's lagged from the seasonal forcing by about 90 days. Over the land, it's something more like 15 or 20 days. The ocean has an enormous heat capacity compared to the ocean. And so the dynamics of the ocean's boundary layer can have a tremendous influence on the magnitude of the seasonal cycle. So these are 2 different cases here where it's exactly the same model. It's a coupled model. But in the one case, I have an efficient wind mixing, an efficient, and I'll get into later what exactly I mean by this, but basically a strongly wind mixed case or a weakly wind mixed case. And this is just changing one parameter, the effect of which is that the summertime mix layers here are much deeper with the stronger wind mixing than with the weaker wind mixing. And as a consequence, the magnitude of the seasonal cycle, which I'm measuring here by the range in monthly mean temperatures, so something very easy to measure observationally, is quite different between these two cases. And yet these differ only in one rather subtle aspect of the ocean's boundary layer dynamics. So the depth of the mixed layer largely determines the heat capacity of the system on diurnal to seasonal timescales. And then on longer timescales, it's the interaction between the ocean's boundary layer and the interior that's important for the long-term storage of heat and carbon. Moreover, many of us care about life in the ocean, either because you're inherently interested in it, because we like to eat it, for instance. And the mixing of nutrients and phytoplankton can control a lot of biological productivity. If the mixed layer is too deep, the phytoplankton get mixed out of the region where there's enough light to stay alive, and so they don't really bloom. You have a bloom in phytoplankton in the spring as the ocean starts to warm, and it's really not about changing the temperature, it's about limiting the depth of the turbulence so that the phytoplankton stay in the well-illuminated upper parts of the ocean. They bloom, but they draw down all the nutrients. Later in the season, it's the supply of nutrients into the mixed layer, mixing from the interior into the ocean, interior ocean up into the mixed layer that determines the productivity of the surface. So the properties of the boundary layer are enormously important for biology. The biology, in turn, can significantly impact the optical properties of seawater. So many of you may have been, say, snorkeling on a reef in the Caribbean or something, where the water is remarkably clear, and you can see just how you can see quite deeply into the ocean. Whereas if you were to go out here into Long Island Sound, where it's a kind of more biologically productive area with a lot of nutrients, the water isn't quite that same clear gin blue. It changes how far light penetrates into the ocean, and in turn, this can change the physical properties of the ocean. A few years ago, we did a study where we looked at changing the optical properties and showed that we could eliminate hurricanes. And finally, when we're in the business of building coupled climate models for doing long-term projections, one of the things we'd like to do is have them be numerically stable enough that they can actually run. And the way that you handle the boundary layer is something that can influence the numerical stability of the coupled system. Okay, so I'm going to spend the next about 20 minutes talking about some of the important physical processes driving the mixed layer and the restratification in the ocean. It is largely externally forced. It's driven in a lot of cases. The stirring is driven by the winds, by the waves. And the buoyancy forcing at the surface is equally important. And it's the interplay between these two that determines the evolution of the boundary layer to a significant degree. It's also an area that's prone to spontaneously growing shear-driven instabilities, the well-known Kelvin, Helmholtz, or Holmboe instabilities. And finally, all of these processes are basically one-dimensional sort of thinking about the boundary layer. In the presence of lateral gradients, you can get shears, you can get eddies, you can get restratification or destabilization driven by the large-scale horizontal gradients that also turn out to be important. But in describing all of these, I'm going to be using energetic considerations to help quantify the balances that we see. And so one of the take-home messages that I want you to think about is that mixing in a stratified environment takes energy. The energy is what constrains how much mixing you'll have. An energy budget is a great way to quantify what's going on. It's not just a one-to-one mapping. It's not quite that simple in that where the mixing occurs matters, but energetics are a great constraint, and that's what we build a lot of our parameterizations upon. Okay. So if there's anybody who's prone to motion sickness, please close your eyes. Okay. Anybody who's not, this is kind of a mental image that I want to give you of what mixing in the ocean looks like. This was a movie that I took on the deck of a ship, the RV Rebelle in the Tasman Sea. And this is a beautiful day. Clear, sunny skies. The wind is howling along at about 30 miles an hour. And we're getting these big waves. They're breaking. They're plunging down. There's a lot of turbulence. It's all being driven from above. Okay? You get bubble injection that's happening over small scales. You can see these kind of rows in some of these cases of kind of bubbles that are being injected around. They're being swooped together and carried around in large overturning cells. But this is a case that I think really captures the challenge of modeling the ocean's boundary layer as opposed to the atmospheric boundary layer, in that this is largely driven from above. You have strong heating from above. This is midsummer. The sun is fully out. There's not a cloud in the sky. Probably have about 400 watts per meter squared of shortwave heating going on. You've got strong evaporation. All the sea spray is driving evaporation. Okay, but all of these are things that we can really understand by thinking about the energetics. And so I'm going to spend some time talking about a Krauss-Turner style bulk mixed layer model. Now this is not new. This particular paper is slightly older than I am that first introduced this, but I think it's a really good pedagogical approach to thinking about the boundary layer. But it's also one that toward the end we're going to come back to and draw a lot of the ideas from in a new approach that we're finding is actually working remarkably well in our climate models. So the basic idea is to note that temperature, salinity, and horizontal velocity are pretty well mixed in the surface boundary layer. And for two of the three of these, that's actually not a bad approximation. For the horizontal velocity, it's not so good. This is an example of a time series of data for basically a chain of thermistors in the Atlantic Ocean, kind of a bit south of us here, in the middle of winter from about 20 years ago in the ASREX observations. And there are, I think, 10 thermistors in the top 75 meters, and then each of these labels are for deeper thermistors. But you can see that these top few thermistors just lie right on top of each other, except during some periods where, in this case, there was a strong wind blowing, and there was a strong storm coming in, and then there's kind of a relaxation. You see some restratification as you go on. So this idea that the surface is well mixed is one that's borne out pretty well. And so I'm drawing it schematically here, where this is the surface of the ocean, and this is density off to the right. So you have a well-mixed mixed layer. You tend to have a jump in density at the base of the mixed layer, and then you have a stratified thermocline, not necessarily straight lines. The idea here is we're going to make the assumption that mixing is basically infinitely fast, but over a finite depth. The depth of this well-mixed region is something that you can constrain from the turbulent kinetic energy budget, and then you assume that the turbulence stops quite abruptly at the base of the mixed layer. And the reason for doing this is it's a very simplified problem. It's one that's easy to visualize mentally. It's easy to reproduce in a laboratory setting. So if you take a beaker of stratified water and you put a grate at the top and you shake it back and forth, you can reproduce this pretty well. In fact, that's where the original Krauss and Turner paper came from. But it's also one where the math is really easy to do, and where the physics is easy to see. And this basically comes back to your introductory physics course. So the idea is we're looking at changes in potential energy. So the change in potential energy from lifting a mass, a distance delta z against gravity, is something that you probably all know, which is just g times the mass times the distance that you move that mass. Pretty simple. Now suppose that I have a profile like this black one, and I do some mixing, and I generate this red profile. The amount of buoyancy is conserved, so the area in here is equal to the area in here. And basically what you've done here is you've taken this dense water down here, and you've lifted it effectively halfway through this boundary layer. The amount of mass that you're mixing is WE, an entrainment rate, times a time step, times the density anomaly of this dense water relative to this water higher up. G is just the gravitational acceleration, and then you're lifting it halfway through the boundary layer. And so this very simple expression describes how much work you had to supply in order to mix this profile to turn the black profile into the red profile. Okay? Now we're going to divide through by the mean density and the amount of time that we ran this over, and this will just convert it into a rate of work that we have to supply. This is a sink. You have to supply a source to balance it. Okay? So what can that source be? So before we get to that source, suppose that instead of mixing, I'm instead applying buoyancy forcing at the surface of the ocean. So in this case, it's a nice sunny day, the sun has come out, it's heating up water right up at the surface. In order to mix that heat down through the water column, I have a certain rate of buoyancy forcing. Again, and the buoyancy forcing includes G buried inside of it. The distance that I have to move it is just half the thickness of the boundary layer. So again, this is just physics 101. How much energy is required to supply the change in potential energy? So those are pretty simple cases. In the ocean, you have shortwave heat that penetrates into the ocean. Anybody who's been out snorkeling knows that the red light, a lot of it gets absorbed at the surface, but the blue light can penetrate down some tens of meters in clear water. And so we want to take that into account because the heating is not occurring in this thin layer up at the surface. Instead, the heating is occurring over an exponentially decaying profile. But again, you can use exactly the same sort of considerations and just integrate over the depth of that profile to say how much energy is required to take an exponentially decaying profile and turn it into a vertically uniform profile. Okay? So, getting a little bit more complicated. Now, suppose that instead of making the surface lighter, you're making the surface denser. Well, in that case, exactly the same consideration applies, but now you're releasing energy. And what we found empirically, both in numerical studies and laboratory studies and a variety of other contexts, is that the efficiency of that released energy in driving further mixing is only about 20%. Okay, so if I were just cooling and this at the surface and all of that energy were driving, scouring at the base of the mix layer, basically you're cooling at the surface, you have this well-mixed region, and then you have some stratification below. That energy that you're releasing is creating a plume, and it's going and scouring up dense water from the base of the mix layer and mixing it back up through the mix layer, so that the buoyancy flux here actually reverses signs. So up here, the buoyancy flux is upward. You're extracting heat from the ocean, but down at the base of the mix layer, you have the buoyancy flux reversing. You're actually bringing denser water up from below, and that's the scouring. And just from the area here, this is about 20%, and there are some geometric considerations that say that's the efficiency of driving additional mixing, additional deepening. Okay. And so now we can put all of these terms together into a mixed layer turbulent kinetic energy balance. So this is the sink here due to entrainment at the base of the mixed layer. We have two new source terms that I'm introducing. One of them is wind stirring. This U star is the square root of the wind stress divided by density. The amount of work that is being done on the ocean is proportional to this U star cubed. And then there's an empirical number out front. Turns out it's relatively inefficient in that most of the energy actually is going into the waves, not into the mixing. But it's an order 1 non-dimensional quantity. If you had velocity differences between the surface water and the water that's being entraining, that's also a potential source of energy in that in homogenizing the velocity, you're reducing the kinetic energy of the system. So that's the second source. And then these are the buoyancy terms that I described earlier with this n star that is either a half or 1, depending on whether, either 0.2 or 1, depending on whether you're stabilizing or destabilizing the system.
Can I ask a question?
Yep.
This is upward entrainment velocity.
Yep.
It's when you model, where can the water go?
Where can the water go?
Go up.
The base of the mixed layer moves down. So this is water moving across a moving interface. So if I go back here,
Yeah, sort of.
right?
Yeah.
So this is W. The water is moving relative to the base of the mixed layer. So it's the rate at which the mixed layer is deepening. Yeah, good question. Thank you. Okay. So we have this balance equation for the energy of the system. And you're going to use this in one of two ways. You're going to calculate the right-hand side. And if the right-hand side is positive, that's used to calculate a rate at which the mixed layer deepens, or an entrainment rate. On the other hand, if the right-hand side is negative, in other words, if you're heating enough at the surface that it more than balances the mechanical energy that you're putting into stir, instead what we're going to do is we're going to say, well, this mixed layer is going to retreat. The water that's passing through is of the same density, and so this term basically drops out. And so you solve for the new thickness of the boundary layer here, H, at which this right-hand side exactly balances. And so this is one of the things that this energy equation, the simple model, kind of illustrates, is that mixing into stratified water tends to be slow, but once you remove the forcing, or once you increase the buoyancy forcing, the turbulence can retreat almost immediately, right? And the balance that you wind up with here is a balance between the mechanical stirring and the buoyancy forcing at the surface. So during the diurnal cycle, we can have something that looks a little bit like this. Now, bear with me, this is not the best picture. I recycled this from an older talk. But this is the seasonal cycle of the mixed layer in depth in black, and then the blue lines are density surfaces in the interior ocean. Down here, this is the temperature on this axis for all of these layers that have any mass in them. Okay, so this line here is the sea surface temperature. This is through the whole diurnal cycle. So here we are. We start off in January. We're cooling. The mixed layer is getting deeper and deeper and deeper. And then we reach some point between April and May, and the mixed layer is retreating because you're heating it faster than you can mix the energy down, right? So we're heating at the surface here, and this turbulence immediately retreats, and the water that is left behind stays in the interior of the ocean. It's pretty well very weakly stratified, because in March, when you had mixed all the way down, all that water had homogeneous properties. Now you're forming a new boundary layer up at the surface, and that boundary layer is getting lighter, and it gets lighter very quickly because it's relatively shallow. This is on the seasonal timescale. If I look here, this is the same figure on the diurnal timescale, and I've collapsed down the axis here of temperature quite dramatically. But there's a pronounced diurnal cycle both in the depth of the boundary layer, it's the black line that you want to look at here, and in the temperature, so that the mixed layer can retreat quite quickly during the daytime, and it comes back the next night when you're no longer, the sun isn't shining, you're not heating at the surface, and so you're convectively cooling. Now it turns out that because of that difference between when you heat at the surface, you have to do all of the work to mix that energy down. When you cool at the surface, you only get 20% of the released energy back. There's a hysteresis. And what that means is that you end up with a systematic difference between two cases. This is an overlay of two figures. The first one has a diurnal cycle of forcing. This bit on the right here is without the diurnal cycle of forcing. The diurnal cycle of forcing gives you a hysteresis. There's an imbalance between the energy when you're cooling and warming, such that the mixed layer is systematically shallower and warmer due to the diurnal cycle of forcing. So this is something that we've only been introducing into climate models in the last 10 or 15 years. Earlier, we would say run and take a 12-hour forcing time step, not resolve the diurnal cycle, partly because we didn't resolve the rather small vertical scales associated with that diurnal cycle. But we're coming to appreciate that there are important physical processes and physical principles that can lead to fairly large systematic differences. This is 2 degrees Celsius between models with and without the diurnal cycle, and we can appreciate why just from these considerations of the energetics. Now, that 20% number is something that you have to modify when the boundary layer gets really deep, in that rotation becomes important. If you have convective plumes that take more than a day to sink, rotation becomes important. And so instead of three-dimensional turbulence, you tend to get turbulence that becomes more columnar, and more of the energy is lost to frictional heating, and less is available to drive scouring of the base of the mixed layer and bringing up dense waters. But this is something that is you can study very easily in a laboratory. You can study it in direct numerical simulations or large eddy simulations, and is illustrated pretty well here. And this is something we have a pretty good handle on based on the depth of the mixed layer, the rate of rotation, and the strength of the buoyancy forcing. So there are complications, but they're not hard to see. It's just essentially a change in the efficiency of these various processes. Okay. So far I've described the externally forced parts of the system. This is now flipping the problem upside down and showing one of my favorite figures, because it illustrates some of the complexities of a boundary layer. But this is now at the bottom. So this is the bottom of the ocean. This is a profile from the Red Sea outflow plume from Babel Mendeb from the Red Sox experiment back before pirates made it impossible to work in the Western Indian Ocean. But it's a wonderful profile in that it illustrates in these two temperature and salinity profiles that there can be different regimes of vigorous turbulence. So down here we have this very well mixed bottom boundary layer. Basically what's happening is the water is cascading down the slope. It's running over rough topography, over rocks. It's generating a lot of turbulence. It's actively stirred. And it's so vigorously stirred that the temperature and salinity are basically uniform in these well-mixed bottom boundary layers. But above that region, we have a strong velocity profile. So the velocity is shown here in the red line, and it's going to come back down to 0 right at the bottom. But the data didn't go quite that far. But up here, above this well-mixed boundary layer, we have a pretty strong shear in the velocity. The velocities here, this is 0.8 meters per second. So this is a pretty strong velocity. And in fact, it's strong enough that if you take the ratio of the shear to the stratification from the temperature and salinity, you get a ratio that's known as the Richardson number. And you might have seen this before, but essentially when this Richardson number becomes really small, it says the shears are large compared to the stratification. You can start to get a roll-up of the fluids. And you can do this. You might have seen little desktop little toys with some oil and some water, and you tip it over, and the water goes kind of cascading, and there's an instability, and it causes these cat's eye roll-ups. Well, whenever this Richardson number is less than a quarter, you can show that that is a growing instability. And so in these shaded areas here, the Richardson number is less than a quarter, and that's also areas where you see evidence of the overturns in these temperature and salinity profiles, right? So it's getting all wrapped up. So this is something that is important at the base, at the surface of this bottom boundary layer. It's also important at the base of the surface mixed layer. And we have ways of parameterizing this. So this is a numerical simulation from a paper we wrote a couple of years ago where we have a stratified fluid, and we start off with flows in opposite directions. You get this kind of roll up into the cat's eyes. And then if you let it go and you keep forcing it, you develop this region of active turbulence here where this Richardson number is relatively small. And so this is something that you can use as the basis of some parameterizations. This is a little bit of a detour from what I'm talking about today, so I'm not going to go into the details here. But the essence here is that by looking at this Richardson number, you can estimate where you are likely to have vigorous turbulence setting in. Okay, so that's showing up here in part in this turbulent mean kinetic energy to turbulent kinetic energy term. Finally, I've been describing the mixed layer as though it's a one-dimensional thing, but anybody who's been out in the ocean and taken temperature measurements knows that you have horizontal gradients, that water has closer to the coast, for instance, might be fresher, and as you go off into the open ocean, it gets saltier, or you have temperature gradients. And in the presence of density gradients, you can have an additional term where if you're advecting light water over dense water, you're tending to stabilize the boundary layer, and so you have to do additional mixing in order to counteract that. Now, you don't tend to get this, you cannot get this from thermal wind shears, but an Ekman transport or sub-mesoscale eddies can both drive significant shears. And so many of you have studied an Ekman spiral in your courses. Well, if you have, generally speaking, you have water that's denser toward the poles than toward the equator. So in most cases, if you have an eastward wind, a westerly wind for atmospheric scientists, you'll tend to be pushing light water over dense water. You tend to make the boundary layer deeper. If you have a westward wind, the Ekman transport is again to the right of the wind, and so you're going to be tending to push light water over dense water. And this can be a systematic effect, but it's happening at large scales. In order to capture this in numerical models, what you really need to do is just resolve the viscosities and the vertical profiles of these shears and allow the model to restratify itself by pushing dense water over light water, or the other way around, depending on the sense of the winds, and then mixing against that stratification. Okay. You can also have the growth of sub-mesoscale eddies in the mixed layer. So you start off with a density gradient here, with lighter water and denser water, put in some perturbations, and they grow over time into eddies, and these eddies have tended to act to slump the boundary layer. And so this is a systematic effect, but it's something that happens at much smaller scales than we tend to resolve. But again, this is something that we've been able to study and been able to quantify, and we have a description for how this works off a wide variety of, in this case, a couple of orders of magnitude in this predicted strength of the overturning stream function versus the simulated overturning stream function. This formula works pretty well. This is work by Baylor Fox Kemper, who's now at Brown. The problem here is that this is occurring on scales of order 1 kilometer. These sub-mesoscale eddies are quite small, and so we've had to figure out how to scale them up to work on the scales of climate models. Okay. And the way that we've done that is by going back to our old friend, the turbulent kinetic energy budget, and by saying, okay, I want to be putting in the right strength of the restratifying term. Sub-mesoscale eddies, because they slump, are always restratifying. And so what I'll do is I'll work on the model's gradients, but with an overturning stream function that's much stronger, because the gradients averaged over the fronts are much larger than the gradients averaged over what the model has. So you amplify the stream function to capture this effect. Okay. I'm skipping ahead a few slides here because in the interest of time, but I'll come back to that point. So now finally, on to the challenge of modeling the boundary layer mixing in ocean climate models. So the basic problem here is we have to come up with parameterizations that just work everywhere, in all situations, under ice, in the tropics, in rivers, everywhere. And we have to do this with horizontal resolutions of order 10 to 100 kilometers that are just huge compared to the frontal scales and the scales of the turbulence. And even the vertical resolutions in the models are something like tens of meters to hundreds of meters. These are really large scales compared to the physical scales of the turbulence in a lot of cases. We have to use, in order to make use of these climate models, a lot of times we're asking questions that require thousands of years of simulations. And in order to make that practical, say in the lifetime of a graduate student, you really need to have models that are able to run it at 10 years a day. So the models have to be pretty simple. And finally, this requires that we couple on timescales of order 1 to 2 hours, which is long compared to the timescales on which the turbulence itself revolves. So this is actually kind of a nasty problem. There are a number of different approaches that people have taken. I've described the bulk mixed layer approach, and this is one that has worked reasonably well in density coordinate models, but not so well in others. People have also used two equation closures, and these are similar to the turbulence modeling approaches that are taken in coastal environments, where your spatial scales are smaller, your temporal scales are smaller. There's less of a mismatch between what you can resolve and the scales of the turbulence itself. And the idea here is that you have an energy equation, but you also need a second equation. An energy equation gives you dimensions of a velocity. We need dimensions of a mixing, and so you need to add in something that will give you a length scale of the mixing or a time scale of the mixing. One common approach is to do this with a dissipation equation. And the challenge here is that these equations are rather complicated, and they evolve on short time scales. So they're not a good match for climate modeling. So to simplify that, there are a couple of different approaches. One is widely used in the European NEMO ocean model, which is to have an explicit turbulent kinetic energy equation, but then prescribe mixing lengths. And so they're explicitly stepping the energy equation, but the rest of the complexity is kind of buried in parametric equations. A more widely used approach here in the US has been to use something known as the K profile parameterization. This is something that was derived from atmospheric boundary layer studies and adapted to the ocean. And the basic idea is you diagnose the depth of the boundary layer based on some a bulk Richardson number criteria, and then you use this to specify a profile of the diffusivity. I'll go into that a little bit more. And then finally, today I'm selling a new scheme where we use an integrated energy equation, exactly like the bulk mix layer, but do this not assuming that the mixing is infinitely fast and infinitely vigorous, but using a finite diffusivity. And with a little bit of work, we were able to actually work out how to solve this energy equation implicitly and exactly in a way that's analogous to the bulk mix layer, but with a finite diffusivity, which has some big advantages, as we'll see momentarily. So the big issues with the bulk mix layer in using climate models, first off, momentum is not perfectly well mixed. As I said earlier, you have Ekman spirals, Ekman shears that can be important in driving restratification. We were able to solve that sort of by adding a few degrees of freedom in a mixed layer where you assume that T and S are well mixed, but not velocity, but that has some limitations. Biological tracers can also have important gradients in the mixed layer, and the reason for this is that the mixing timescales are not all that different from some of the timescales on which biological processes occur. And the third problem, and this is the one that really is the big issue for most climate models, is that you can get spurious mixing that occurs whenever the depth of your boundary layer doesn't exactly coincide with the levels of your model. So in a z-coordinate model, if you have a 10-meter resolution, your boundary layer can be 20 meters deep or it can be 30 meters deep, but it can't be 25 meters deep, effectively. And so this, in practice, was found not to work very well back in the 90s when this was tried. In isopycnal coordinates, the layers are moving around, and so it's not a big deal to have one of them follow the base of the mixed layer. But then you're left with the water that's left behind, and so you have to come up with some ugly ways of trying to move it into the interior. And so, although this has had some success, it has been rather limited in its application. Skip through the two equation closure models to the KPP parameterization of large et al. And the idea here is that the bulk Richardson number determines the depth of the boundary layer. Basically, you go down through the water column until there's enough of a density contrast between the water average through the column and the water at the base of the column that is enough to stabilize the large-scale shears. You then specify the mixing within that boundary layer down to this depth h with an empirical form that scales with the strength of the wind and the buoyancy forcing, and this profile that's chosen basically to go to 0 at the surface and the base of the boundary layer and to have 0 gradient at the bottom. This is the simplest form that does that, times some stability functions that nobody ever really understands. Okay, Bill Large understands. I don't. I've tried reading this paper about 5 or 6 times, and I think I understand it for about a half an hour, but it's really hard to wrap your head around this thing. And the biggest problem here with KPP, first off, this boundary layer is based on the properties at the beginning of the time step, not the effects of the forcing. And secondly, there is no energy equation. It's sort of buried somewhere behind this, but there's no explicit energy equation. There's nothing to constrain this. So as a review, this is great. As a pedagogical paper, I don't really care for it. And what really prompted all of the work that I've been describing today, we were using KPP in our new coupled climate model, and we were getting these weird sorts of instabilities where you get spontaneous growth of sea ice. So this is a section of the Arctic Ocean. This is January 1st. This is January 4th. And for reasons that made no physical sense whatsoever, we were getting this spontaneous growth of sea ice from about 1.5 meters to 3 meters over the course of 3 days. And sea ice doesn't work that way. It's not supposed to work that way. And since I was building the sea ice model, at the time people came and knocked on my door and said, your sea ice model is no good. Okay, I'll take a look at it. So we looked at it, and what we found is that there was an instability in the boundary layer where, because we were diagnosing the boundary layer depth based on the properties at the beginning of the time step and not taking into account the strength of the forcing, that there was a lag. And so you get a shallow boundary layer subject to strong forcing that would then lead to a deep boundary layer. This is going from 10 meters to 90 meters and then back again. And this weird coupled instability. So every 2 time steps it's going back and forth. It's basically shaking itself apart. And that's coming from the explicit approach for calculating this boundary layer, which prompted us to develop this new integrated energetics approach to determining planetary boundary layer mixing. So first off, there's only one small transformation I need to make, and that is, instead of working in depth space, so this is an expression for the potential energy, we needed to convert into pressure space, because when you mix, the water column as a whole can change its height, but it doesn't change the hydrostatic pressure at the top and the bottom. So based on this exact result, we're basically able, and I'm not going to go through the equations in the interest of time, but to say if I mix at this interface, well, that's going to, if I have a finite diffusivity throughout the rest of the column, it's going to change the temperature and salinity both here, but it's also going to be implicitly coupled throughout the rest of the boundary layer. In fact, in a surface boundary layer, this might be a very large diffusivity. So mixing here is like entrainment, but this entrainment can also change the properties throughout the water column. And so what we're looking at is how much does changing the mixing at one point change the specific volume throughout the entire water column. And from that, we can calculate the energy change. So you start off at the surface, you have a certain budget of energy, and at each point, you calculate how much energy is required for a certain level of mixing. Okay? So you have a profile of a diffusivity that's kind of your first guess. And these are the equations to tell you how much that energy changes. And I don't expect you to read them. The upshot is we have it's a linear problem. We can solve for these. Okay? So the idea is you start off with the turbulent kinetic energy at the surface. Okay? And you move down with some first guess at what the diffusivity is going to be based on the strength of the turbulence coming into that level and maybe say the distance from the surface. The exact form of this doesn't really matter. The upshot is you have some guess at the diffusivity, and then you calculate what would the energy consequences be of that diffusivity. If you have enough energy to supply that, keep it. If you don't, reduce the diffusivity to the point where you have the energy to support it. Okay? Now, the potential energy change calculation has to be fully implicit, but we already know how to do that. You could recover a bulk mix layer by specifying your target diffusivity to be infinite. An infinite diffusivity just means you homogenize water, and that has a finite change in the energy. Mixed water doesn't do anything more. Okay? So I could choose this to be infinite. In this case, I'm choosing it to be finite in line with what's something close to what's done with KPP. Okay? And when we do that and apply this to our coupled model, and we look back at these 2 points, this is the strength of the variability of the boundary layer thickness from one time step to the next. The red line was KPP. That was the one that was having these big oscillations. When we do this, this is now fully implicit, and it just settles right down. All of our instabilities went away. And what's more, when we look at idealized test cases, so this is a test case with, we're heating at the surface and we're applying wind forcing at 2 different resolutions. This is 0.4 meters and 10 meter resolutions with KPP and this new energetic planetary boundary layer scheme. What you see is that there's a remarkable lack of dependence on the resolution with the new scheme. Basically, if you're mixing with an energetic constraint, if you change where you're mixing, it doesn't really matter so much because the amount of work that you've done over time doesn't change. It's constrained. Whereas the fact that KPP doesn't have a boundary layer scheme means that fitting these empirical forms gives you some significant sensitivity of the surface temperature to the resolution. And so we're actually really pleased with what this does. We can also do the same thing with a boundary layer which is convecting. You're cooling at the surface and it's deepening. And both of these schemes are able to capture this case pretty well. In this case, there is some resolution dependence to the value of the temperature in the topmost layer, but I think a lot of it is just that we're maybe not mixing as rapidly enough at the surface, but the deepening here is remarkably independent of resolution between these 2 cases. Much more so here if you compare the depth of this mixed layer here and here with what we're getting with KPP here versus here. Right? So this and this are pretty similar. And they almost have to be similar because you have the same budget of energy to use. Whereas KPP, there's some significant sensitivity to the depth of the mixed layer. And then similarly, for a case with wind forcing alone. So this is mechanically stirring into stratification. Okay. And so finally, we can look at what this does on climate scales. So this is the minimum monthly mean mixed layer depth. In other words, you take monthly mean properties and you say how far down you have to go before you get a certain density change. This is what's observed. We're really quite pleased with what this energetic planetary boundary layer does in this metric, which has not a lot of sensitivity to the mean state of the atmosphere, but really has a lot to do with what's happening in the boundary layer. And we're reproducing these patterns quite well, much better in some ways than KPP. Whereas if you look at the maximum mixed layer depth, this is now driven by free convection, mostly. In other words, how much have you cooled at the surface? And in this case, both of the models are in a lot of places quite similar. You're extracting the same amount of heat. You do the same amount of deep convection. So we're pretty pleased with how this is working. And finally, we can look at a figure that I showed related to the one I showed earlier, where we're looking at the magnitude of the seasonal cycle. Again, this is something that has to do mostly with the boundary layer physics and less to do with the state of the atmosphere. And we're able to reproduce the observed range of sea surface temperatures much better with this new scheme than with KPP. So we have some empirical reasons to be quite pleased. Okay. So in summary, if there's only one thing that you take away from this lecture, it's that energetics constrain boundary mixing, right? Mixing into stratification takes energy, account for the energy, and do some reasonable-ish things with how quickly you're mixing, and you'll do pretty well. We have a new scheme, which we think pulls in a lot of the ideas from older schemes. It emphasizes an energy budget. It allows for finite rates of mixing, not infinite mixing, and yet stays mathematically tractable to the point where we can look at the evolution of that energy implicitly. And it seems to work very, very well. We're quite pleased with it in a series of idealized and realistic test cases. what's more, it works for any coordinate system. Whereas with a bulk mix layer, you had to track the base of the mix layer. In this case, if you have, say, a Z coordinate model, you're mixing over a finite depth. That last cell, you don't ever actually have to calculate exactly where the base of the boundary layer is. You're only calculating how much energy you can do for mixing at interfaces. You never actually have to diagnose n squared, any local value of stratification, which for those of you who are observationalists is a big deal, because what do you mean by the stratification depends on how much you smooth your data. And if you don't smooth it at all, you wind up with crazy values. If you smooth it a lot, you can wind up with something that's fairly robust, but now it's smoothed over length scales. The fact that we're just saying how much does the energy in the column change, not what happens locally, is actually a big deal for the stability of the system, right? And so this is something that's easily extendable to other processes. And so we really see this as not the final solution to this problem, but really as a framework into which we can build in new ideas. Ideas about how, for instance, sub-mesoscale stratification might happen. So instead of giving an overly large stream function, maybe the way that we do it is we use the stream function based on the model's observed gradients, but then have an additional sink of energy that is accounting for what's happening at very small scales. We can incorporate things like Langmuir cell-driven mixing, wave flow interaction-driven mixing, by adding a different flavor of energy that might have a different decay scale. Langmuir cells are big coherent vortices. They tend to transport turbulence down more efficiently than just mechanical stirring. And the way that you would account for that is by having a budget of energy that is able to be swept down greater lengths before it's consumed. We should be able to use this to include more effects of breaking surface waves. There's even been some speculation that a little bit of energy leaks out of swell to drive mixing. And that's also something, again, because you quantify it as an energy source, we should be able to fit into this system. And we're also looking at how this can be applied to the bottom boundary layer and mixing in the interior by looking at the integrated consequences of energetic consequences of mixing, as opposed to a local relationship between a local diffusivity and a local buoyancy flux. So hopefully this has given you a bit of an overall flavor of some of the physics of the ocean's boundary layer as an externally forced system, some of the differences between the ocean and the atmosphere. The biggest one, by the way, when I first came to GFDL, I was hired by Jerry Mullman, and he said, you know, you oceanographers have it really easy. Well, why is that? He said, well, the ocean is dry. By which he meant that we don't have the moist phase changes that dominate so much of the dynamics in the atmosphere, the evaporation, the formation of clouds, and interaction of turbulence. So it's relatively simple, but the fact that it's being driven from outside means that what we want to emphasize in our boundary layers is a bit different than what you want to emphasize in the atmosphere. It's not internal constraints, it's careful consideration of the overall budgets of the external forcing. And so we see this as kind of a nice paradigm that we can use, hopefully one that people will find relatively easy to understand because it's drawn directly from some pretty solid physical principles, and where people can contribute. We don't think this is complete. What we see is this is an opening to try to engage a broader community in helping to improve how we describe the broad range of processes that are going on in the boundary layer. Thank you very much.
Maybe one or two questions before we break. What?
So do you solve the diffusivity layer by layer, or you need to couple all the layers together?
All the layers have to be coupled together. However, so that was the long set of equations that I deliberately glanced over. You're able to do it as a cumulative sum. And so in the same way that a tridiagonal equation is something that you can solve with a one pass down through the column, you're taking into account if you change the temperature in a layer, that will lead to changes in all of the layers above. And you do that as kind of a cumulative thing in the same way. So it's integrated throughout the entire water column. But you don't have to go through and for each new interface, go back to all the other layers. It's one calculation for each interface, which is what makes it practical.
Yeah, so the formula is based on that entrainment velocity, basically, right?
It's actually
The diffusivity. You had the formula of the diffusivity as a function of the kinetic energy. Is that in principle similar to the entrainment velocity?
they are closely analogous. We don't actually move any water around at all with this. So if you were to apply this, say, in a density coordinate, you keep all the water in place, do all the mixing, and then remap. Or if you're doing this in a z-coordinate, you keep all the water in place, or pressure coordinate, you keep all the water in place, you do the mixing. So whereas in order to get, with the bulk mixed layer approach, we're having to move around layers to try to track the base of the mixed layer, there's no water that has to move here. And I mean, these are incredibly perceptive questions, because you've just gotten right to the heart of why this works for a wide variety of coordinate systems quite well. And that's one of the things we're really excited about, because we're trying to develop, for our coupled climate models, we're trying to develop numerics that will work for a wide variety of different coordinate systems. So we have z-coordinate, we have hybrid z to density coordinates or sigma coordinates. And so we'd like to have things that are basically invariant to how you treat the coordinate system. This is capturing a lot of the ideas of the old bulk mixed layer ideas, but without actually having to have this moving boundary layer, which is it's one of the biggest points here, and probably one that I should have emphasized a bit more.
Okay. Yeah, for the old bulk model, we have say some situations to adjust the conditions for the whole for the initial to the end. My question is, using a new scheme,
Yeah.
Would the result be different? Would the result of the adjustment be different, or in the meantime the speed of course is different? It takes longer because the old scheme is linear. So my question is,
Yeah.
what's the difference between the results? If we use under the same condition, if we use the old system, we get a result. Using a new system, we get another result.
Right. So this actually illustrates, it's a subtle point, but one of the things that we can get is you get this surface cool layer or surface warm layer. Overall, because you're putting the same amount of energy in, the results are pretty similar. The details are where it matters. And it turns out, when we're talking with some of our colleagues at NCEP, who are trying to develop forecast models, one of the things they're really concerned about is whether we can capture the diurnal cycle of the skin temperature. They don't really care about the average ocean temperature over the top 20 meters. They're really looking about the top, the skin, this evaporative layer, this radiative layer. And so the fact that we have a finite diffusivity, the energy budget means the depth of the mixed layer is going to be pretty similar. We've done the same amount of work. We've done the calculation carefully. But with a finite diffusivity, we're allowed to get a cool skin layer, or we're allowed to get a surface warm layer. And so that's, from the standpoint of application, that's this weird little feature is one of the biggest, most important differences between the two. But overall, they're going to behave pretty similarly in the limit that you had lots and lots of resolution. If you had a z-coordinate model and a bulk mixed layer with, say, 10 or 20 meter resolution, where you either perfectly homogenize 20 meters or you perfectly homogenize 30 meters, that's a really big difference, which is why bulk mixed layers never caught on for use with z-coordinate ocean models.
We probably should break for lunch. Anyone who wants to keep asking questions is welcome to go lunch for that. And